Hello, Assalamualaikum. Good day, everyone. Hopefully, everyone is in good health and safe from any virus. Okay, so we are going to continue with our lecture. Today, we are going to enter new subtopic, which is curved beams. So, as you can see on the diagram, that is what I mean by curved beam. For curved beams, we assume that the cross-sectional area is constant, although the beam is curved, but the cross-sectional area is constant. Okay, and it has an axis of symmetry that is perpendicular to the direction of the applied moment. Okay, so if you can see right here, the moment applied is along the y-axis. As you can see, this there is a y-axis over there. So it is the moment applied is in same direction with the curve. Okay, so when this happen, if you look at here, we assume that the cross-sectional area or shape is a symmetry. Okay, where the left hand side and the right hand side is the same. Okay, so let's focus on this diagram. So you can see that there are so many parameters that we can identify here. The first one is that I want to mention is R. R is the neutral axis. That's the important part. R is the neutral axis. Okay, and the neutral axis may not or may we call it align with the centroid. In this diagram, it is not aligned. So this is the line for the neutral axis. This is the cross section, okay? And the centroid is a little above the neutral axis. And you can see that the moment is applied to this direction, okay? And then we have parameter, yes, the R is the radius, and the neutral axis is actually like a curve according to the curve of the beam. Right, so inside, if you look at right here, when we focus on a particular element in the cross section, which is dA, if we are interested at the stress at that point, we may have an equation to calculate the stress at that point. So we need to know the radius, r, the small r, okay. The small r and also the y, okay, the small r and y to where y is the perpendicular distance from the neutral axis, okay. And also we have another parameter that I forgot to mention before, which is the r prime right here, where this is the distance or the radius of the centroid from the origin. This origin is the origin of the curve beam, and E is the what we call it, eccentricity between the neutral axis and the centroid, okay. And A, we have area also. We need to consider the area as well. So this is the formula to calculate R, okay. So we have area, cross-sectional area. We have this parameter, the area over R across the area, and we have R, the big radius right here, okay. and that's how we calculate the value of R. So right now, for other type of geometry or cross-section area, these are the formula for the formula I mentioned just now. So each of the A, the formula is R equal to A over dA over R. Okay, so this one is this one, and area is right here. So we can use this table if we have this kind of shape of the cross section, right? So, and to calculate the stress within the cross sectional area, so the R right here is the location of the interested point where, for example, we have this kind of cross section area, cross section shape, and this is the neutral axis, and we are interested at this point. So you need to find the R. The R is not this one. This one is Y, and the R is actually, let's say this is the big R. This is the origin. So this is the R, the small r. Okay. And you need to know the R prime as well. R prime is the centroid to the origin. Alright, so yes, this is the formula. So you can use either this one to calculate the stress, or this one. This is the stress at this point. Okay. So we go to the example 6.35 to try and to understand how to solve this problem. So the curved bar has a cross-section area as shown. So this is the cross-section area. Okay. So 50 times 50, and we have a triangular shape as well. So we need to separate the two, a square and a triangle. Okay. And if it is subjected to bending moment of 4 kilonewton meter, determine the maximum normal stress developed in the bar. So when we need to calculate the maximum normal stress, it means that we need to find the furthest distance. Within the cross section from the center. So either this line or this point. Okay. So okay. So when I mentioned about R, I forgot to tell you that R is actually the radius of the neutral axis. So we need to find the neutral axis. We don't know the neutral axis yet, so we need to find the neutral axis by using this formula, and then we know we can use the formula to calculate. Okay, and at this point we can only measure the centroid. Okay, the centroid. So what we need to do first is we calculate the area, the cross-sectional area. Okay, this is for the square and this is for the triangle, and you get the value. And then we need to determine the centroid, the location of the centroid, which is R. location of the centroid is determined with reference to the center of the curvature point. So actually I think this is should have like that. So this is the centroid. If you can see right here, we have R prime right here. So this is the one that we calculating right now. So we use this formula to calculate the centroid. So this formula is almost like the neutral axis, but it is different because we are in curved beam. So how to calculate is we find the area, and also we find the this R. So why sigma? Because the cross section has two shapes, so we need to consider individually. So this centroid and this centroid, and then you total it, and then divide by the total area, and then you get the radius of the centroid. Okay, and then after you get the centroid, all right, and right now we can calculate the R. So before we calculate the R, we need to find this component first. Okay, the integration across the area, dA of R. So for the rectangle, where do we get this from? Is from the table. So for rectangle we use this formula, and for triangle we use different formula. So the formula is right here. This is for rectangle, B ln R2 over R1. So R2 is this one, R1 is this one. Okay, make sure you measure correctly. And for triangle, R2 is this one and R1 is this one. What is this line? This line is actually the center of the curved beam, center of the curved beam, the origin. Okay, the origin right here. Okay, so as you can see, we can use this value 200, 250. Yes, 200 and 250 is for the rectangle, and you can see right here, yes, 250 over 200, right, a millimeter, 0.25 and over 0.2 meter. So we use the formula right here. Okay, R2 over R1, right. So B, what is B? B is the width, the width, which is 50 millimeter or 0.05. So we get the value for this component. What should I call this component? The integration. The integration is equal to 0.11157. And for the triangle, we use the formula for triangle cross section, and then we can get this value. We have minus right here. Why we have minus? So because we minus B right here. Okay, the formula is quite lengthy. Okay, so we finally get the value 0.002887 meter. Okay, that's the value for triangle. And then after we get this, we can calculate the radius for neutral axis. So we total up the area we have calculated, which is right here, and divide by the total of the integrations, this one plus this one. Okay, and then we get the radius 0.23142 meter. Okay, after we get the neutral axis. Okay, so next is we just use the formula to calculate the stress at point B and at point A. So point B is right here, point A is right here. Okay, that is where the stress, like I said just now right here, where the maximum stress occur. So you need to measure the location and the radius, the RB, and RA, RB, RA. So maybe there's some problem right here. Why there is RB right here, it should be RA. Right? So RB is 0.2. The big R is right here. RB is 0.2. Right. Yes, 0.2 right here. And RA is 0.28. Okay. So you can see RB is 0.2, 0.2. And RA is 0.28, 0.28. And what is this value? 0.00166. 0.00166 right here is the centroid minus the neutral axis. So the centroid is, we have calculated right here, the centroid radius. So you minus with this, you get that 0.00166. Okay, and the area, and then finally you get the answer. So if it's negative, it will be negative, which is compression, and for positive is tension. Okay, so now we will learn about next subtopic, which is stress concentration. So this is the third time we learn about stress concentration. So before this in tension and compression, and then in torsion, and right now in bending. So the maximum normal stress at each of the discontinuities. So this is the continuities we have changed in cross-section area. So maximum normal stress occurs at smallest cross-section. Okay, this has been learned before. So like usual, we need to find value of K based on the dimension of the component or of the object. The maximum bending stress is determined by using this formula. Okay. So M is the bending moment, C is the maximum radius, I is moment of inertia, K is the value, this value, the stress concentration factor. Okay, and then we can find the maximum stress inside this component. So let's try this simple example. Example 6.26. The transition in the cross-sectional area of steel bar is achieved using shoulder fillet. See, there's a fillet right there. If the bar is subjected to a bending moment, okay. Now let's understand that the moment is in this axis, so in this direction. So that means the rotation is like that. Okay. So hopefully you understand how the moment is applied to the specimen or to the object. Okay, from the geometry of the bar, R over H. So we need to find R over H, W over H. So R is the radius of the fillet, H is the distance of the width of the small area, and W is the bigger width. and 0.2, 1.5. So by using these values, you can get the value of K. 1.5 is this curve, this one, and 0.2, we connect with the 0.2, so this is the 0.2 right there, and then you can approximate what is the value, which is 1.45 if I'm not mistaken. Yes, it is accurate. 1.45. Okay, so we have obtained the value of K, and then we just simply put everything inside the formula right here. And K is 1.45, M is 5 kilonewton. Make sure that the unit is correct. Although we put 5 only, but you need to understand the unit. If 5K, maybe it's better for you to write 5,000. And C is 0.04 watt, 0.04 meter. Why 0.04? Because we are considering the smaller cross-sectional area, and the center is right there. So Y or C is 40 mm, which is 0.04 meter. And then I is the moment of inertia, 1/12, 0.02. This is the cross-section area, 0.02 times 0.083, power of 3. Okay, because 0.08 is perpendicular to the axis of bending. Alright, so finally we get the answer, which is 340 megapascal. This result indicates that the steel remains elastic since the stress is below the yield stress. So, given the yield stress, the component is still in elastic deformation. Alright, so we finish with this example.